Hello F Sharp. Welcome to another video. I am absurdly excited about this next series because what we're going to be doing is a lot of application. And what we're going to do is we're going to take an algorithm that I use extensively at work, start with a naive implementation of it, and then go through the process of benchmarking it, profiling it, and improving it. And what I'm hoping from this, that you will take away from this exercise is the ability to kind of look at code, run the benchmarks, look at profiling data, and then be able to make improvements to algorithms. And I think this is one of the most important things when it comes to writing fast code is that you're not doing it in a vacuum. You're not guessing at what you're doing. What you do is you're able to use data to inform what changes you need to make to your code. So this is going to be a series. This is going to take me a few weeks to get through because I want to be able to go through each layer of improvement and unpack it for you so that you understand what my thinking was when I made those changes and that you can follow along. The idea is that you're going to be able to also develop an intuition when you look at code and then being able to validate that intuition and make improvements. So like I said, let's jump into this. I am absurdly pumped. Now, the algorithm that we're going to be working on is a topological sorting algorithm. Topological sorting, and on the screen right now, you should be seeing the Wikipedia article. What it is, and I'm going to scroll down here so you can see the visualization because it'll make more sense. What a topological sort is given a graph of nodes and edges, you want an ordering of nodes such that if you follow that ordering, you know that by the time you get to a node, you will have visited all of its parents. And what we're seeing on the screen here is a very simple little graph. We have 5, which then is connected to 11, 7, which connects to 11 and 8, 3, which connects to 8, and then you see 11 connects to 2 and to 9, 8 connects to 9, and 3 also connects to 10. So what we want, what a topological sort is an ordering of these nodes such that you will visit all the parents before you visit a child. And this lists out several different sortings that are valid topological sorts. And like the simplest one when we look at this is say like, hey, I'm going to do 5, 7, 3, then 11 and 8, then 2, then 9, then 10. You could also do 3, 7, 5, 8, 11, 10, 9, 2. Both of those are valid topological sorts. An invalid topological sort would be if you started with 9 and then did 3, then 7, then 8. And the reason for that is if you visit 9 first, you will not have visited 8 or 11 yet. So the idea is you want to visit these in an order so that you know that all the parents have already been visited. Why does this algorithm matter? This problem actually comes up in the real world a lot. And a classic example is when you have a project and you have a bunch of different tasks that you need to accomplish. And you can think of the tasks as nodes. And the edges are like, which task do you do, like the dependency on the tasks. Like, hey, task A needs to be completed before task B, but task C can be completed completely independently of A. And so it's the idea of like, hey, given a bunch of work that needs to be done, what order of the work, give me an order of the work so that I have accomplished all the dependencies by the time I get to it. And there's lots of other examples of problems like that, but that's just a really simple example. It comes up all the time, like in databases when you have like an execution path and you're like, hey, what work do I need to do in what order? It's very useful. In my case, I have, well, I'm not going to go into my case exactly, but it's manufacturing processes and like one process feeds into another. And sometimes I need to find a sort, an ordering of those processes so I can run another algorithm after I've run this to be able to compute some other things that I'm interested in. So we are going to be looking at this topological sort. And so a naive implementation of this, that's what we're going to start with, because one of the most important thing is when we're doing this benchmarking and profiling, we don't want to guess at what is slow. We want to know what's slow. But before we go around changing things, it is critical that we establish a benchmark for where are we at now. We also need to establish how fast do we need to go, because you need to have the end in mind. You need to know, like, hey, once I get to this level of speed, in this case, I can stop. I don't have to keep going, because benchmarking and profiling is this infinite hole. You can be doing it ad infinitum. So you need to say, like, once I've reached this level, I can stop. Now, in my case, we have a simulation. Well, technically, we have a simulation engine. And to run like a year's worth of data, there's approximately 1 million iterations that happen inside of it. And in each one of those iterations, a topological sort is something that you have to do. Now, the graphs can change with each frame, so you can't like pre-compute everything ahead of time. No, the shape of the graph is changing over time. So that's why you have to do the sort every single time. You need to do it 1 million times. And ideally, the end user is someone that we would call a modeler, perhaps an analyst, but they're building a model and then they're running it through the engine. Ideally, they have a near real-time experience, and that way they're able to stay in this state of flow as they're working on it. If they're having to make a change to the simulation and then it takes 30 minutes to run it, that's completely unacceptable. Ideally, we want them to be able to make a change to the model and run it and get results back within a second. That would be the absolute ideal. Worst case scenario is 10 seconds, because 10 seconds is long enough. I mean, fast enough that you're not starting to think to like, oh, I should go refill my coffee or something like that. Well, maybe it depends on how close your coffee is. But worst case performance that is acceptable would be 10 seconds. Now that's for the total simulation, and the topological sort is just a piece that occurs inside of it. It happens to be the hottest piece of code, and we know we need to run it 1 million times. So 10 seconds, ideally 1 second, 1 million times. Okay, so that means we need to be able to run each iteration of each step of the simulation in approximately a microsecond. That's pretty bananas fast. That would be for the ideal case. In a acceptable case, you can take 10 microseconds. Now that sounds, like I said, that still sounds pretty darn fast, but computers are outrageously fast. So I am targeting my ideal, like I know I'm done if I can get this topological sort down to in the range of 500 nanoseconds, which again, I don't know if that's technically possible, and I don't accomplish that in this series, not yet. Well, not as of recording, and perhaps this is going to be the fun challenge that I throw out there for the community is like, hey, can you get it to go this fast? Because I'm still not there. I'm close, but I'm not there. So some other information that we should know is that the size of these graphs is not, it's bounded. The largest one I would ever deal with would be approximately 20 nodes and 30 edges. And that is on the far end of things. Most of the time it's actually like 10, maybe even just 5 nodes. So for the purpose of this, I'm going to use 20 nodes for the size of the graphs that I'm going to be testing against. But I'm just kind of giving you an idea of like the size of things that we're dealing with and the speeds that we're wanting to accomplish. And again, this is ongoing work for me. I'm still working on making this thing go even faster than the fastest thing I have here. And part of the reason I'm doing this is getting feedback from people saying, hey, Matthew, you're doing something absurdly stupid here. Do this and make things better. But let's start with the naive implementation and see where we are from a complete baseline without any optimization. Just like, hey, I'm going to take the algorithm as described here, and I am going to implement it in F sharp in the most F sharp idiomatic way possible. And there are several different algorithms for computing topological sorts. The one we are going to use is Kahn's algorithm. It is one of the best in terms of runtime complexity and just simplicity of implementation. So, and the nice thing about it is that the result you get from it will tell you, is it actually possible to get a sort or not? And sometimes in the graphs that I'm dealing with is that, hey, there's a cyclic thing, so it's not actually possible to get a topological sort, and then I have to revert to some other code. But 99.9% of the time, it is possible to compute a topological sort, and we are using Kahn's algorithm. So let's come back here to the code and let's do the naive domain. So what I'm doing is this completely naive approach. And so if you're like, Matthew, you're doing something so stupid, I know. Well, I might not know, but this is just our baseline. So here I'm going to say, like, hey, I have a type, it's a node, and it's going to have a name. I'm going to model that as a string. Incredibly simple. An edge is simply two nodes, the source node and the target node. And I'm going to come back here so you know what I'm talking about. When I talk about an edge, in this case, the source, in this case from 5 to 11, this edge, this arrow right here, the source would be 5 and the target would be 11. And so it's parent to child is how that relationship works. And then I say like, hey, I have some type aliases here just to describe what I'm doing. Like sources is going to be a map where I have a node. And for that node, I'm going to give all the end-bound edges. So these are the edges that are pointing to the node in question. And targets would be, for a given node, what edges are leaving that node. Let me come back here. So for 8, for the sources of 8, it would be 7 and 3. And the targets of 8 would be 9. The sources of 11 would be 5 and 7, and the targets of 11 would be 2, 9, and 10. So that's what that collection is modeling there. And then I'm going to say a graph is just a single case to you, and it's just a list of edges, just something incredibly simple. And I'm going to scroll all the way down here at the bottom to say, okay, here is my sort algorithm, right? Where it's like, hey, I'm going to get a graph, and then I'm going to create this like set of edges that are inside of it. And then I have this function, which is the graph decompose. And what that does is it takes all the edges, it finds the nodes that are sources. And what I mean by that, sources in this case are nodes with no parent. So 5, 7, and 3 would be, 5, 7, and 3 would be sources in this graph because no other nodes are pointing to them. And I need those to jumpstart the Kahn's algorithm. I'm going to switch back. It also computes the sources and the targets. So there's a lot going on inside of here, but basically it just looks through all the edges, finds the nodes that are sources, and then creates those two different maps that I need for saying, hey, for a given node, who points to me, and for a given node, who do I point to? And then it goes through this loop logic where it just kind of keeps going through until it's done all the processing. In this case, this is the loop, just a recursive function, sources, targets, the remaining edges. So as the Kahn's algorithm runs, what it's doing is it's actually removing edges from the graph, and that way it's able to identify, hey, have I visited all the parents of a given node or not? And to process, in this case, let me make this smaller so we get more space here. To process is a list of nodes that I still need to do some work on, And then sorted nodes, my apologies, sorted nodes is a list of nodes that it's the accumulators. Like, hey, this is the list that I'm putting together of like the order that you should visit nodes. And what it does is it says, are there still nodes to process or not? If that list is empty, then it's going to say, hey, check that I have removed all the edges from the graph. And in the cons algorithm, that's the validation to say, do you actually have a graph where I can compute a topological sort or not? If there are edges left, then you actually have a cycle somewhere in that graph. And I can't give you a sort back. If it does, if there are no remaining edges, then what it does is it takes that list of sorted nodes and reverses it to give you the order that you want. Because with a list, I'm just prepending nodes onto it to build up the edges. To build up the sorted order. And then from here, what it does is a little bit of logic. It's on the cons algorithm. I'm not going to unpack that completely, but suffice to say what it does is it says, hey, I'm going to take this node. I'm going to remove edges. Is nothing else pointing to this node or not? Okay, then I need to process it. But that's what this loop is up here. If you want to understand this more, I recommend reading the Wikipedia article and then coming back to this. I tried to do as close of a translation as possible, but in a pure, immutable functional programming style. I'm not saying F# style. I'm saying pure functional programming, immutable types all over the place. So that's a little introduction to how this logic is working. Now let's go to the actual benchmarking code that I have. And so what I did, and let me open this up, is I have several different versions here that we're going to unpack in the next few weeks. But we're only going to go over version 1 to establish our benchmark today. And inside of program, what I do is I create a module data. And this is where I'm going to pre-compute all the graphs that I want to solve. In this case, my graphs are going to have 20 nodes. And I'm going to be generating random graphs for it to solve because I don't want my profiling and benchmarking to bias me toward a specific graph. I want to have to solve a bunch of them, but they're all of a given shape. I don't care about anything outside of these bounds because for my problem, they don't occur. I'm going to compute 1,000 graphs. I'm going to use the same random number generating seed for all these different data, and you're going to see why this is important. And then I have this array for random edge count. And the reason I need this is because I need a weighted distribution. Most of the time, an edge will have just a single, most of the time, a node will only have a single edge, a single arrow edge coming out of it. Sometimes there will be 2 edges, and occasionally, 10% of the time, there will be 3. And how I use this will come up. But basically what I do is I say, hey, for this given node, how many edges do I want to create coming out of it? And I will just randomly pick one of the indices in here, and that will determine that's how many edges I'm going to randomly generate coming out of it. What I do here is I say, hey, for version 1, this is where I'm going to put the data for it. I create the random number seed. I create the random number generator using the same random number seed that I established up above. And the reason this is important is because I'm going to create different, for each of these versions, I create my own little domain representation for it, but I want the same graphs. I want to make sure that I'm benchmarking against the exact same set of graphs for each of these methods. So I need to be able to randomly generate the same graphs every single time. And that's why it's important for me to create a new random number generator, but with the same random number seed. I create the set of nodes that I'm going to be, and in this case, the nodes are the same for all of them. It's just the same 20 nodes, but it's the arrangement, the graphs made from those nodes that are going to be different. And so this is going to be a list of graphs that I'm generating. So for 1 to graph count, I am going to randomly generate a set of edges. And the way I do that is I'm going to go for each node, except the last one, because the last one I need to be like the terminating node, like nothing leaves the last node. For each of them, I'm going to choose a random number of edges coming off of that given node. And this is where this weighted distribution is. I'm going to say, hey, how many random edges am I going to generate? I then randomly, for each of those, I'm going to randomly pick a target node. And that target node has to be a node farther down than the node I'm on. And that way I can guarantee all of these graphs that I'm going to generate it is actually possible to compute a topological sort for them. I then create the edge. I make sure that I only have distinct edges, and then I put that into a graph. So this is how I'm randomly generating 1,000 graphs to test against. Now for benchmarking, I create my benchmark class. In this case, I am annotating it with memory diagnoser, and this comes from benchmark.net. And I'm saying, hey, I want some hardware counter information. So this is going to tell me some things about how the CPU is behaving and how CPU friendly my algorithm is. Now, when you do this, you actually have to run the terminal in as administrator. So you can't so be aware of that. So when I show you the results, and if you try to duplicate it, make sure that if you're going to run the benchmarks that your terminal is an admin. Otherwise, it's going to give you an error and saying like, hey, you need to run this as admin. That's what's going on. And then for my benchmarking, what I do, and I'm just going to go over V1 here because that's what we're establishing our baseline today. I declare a result as mutable because what I'm doing is I'm making sure the CLR believes that it needs to do all the work because the CLR is insanely smart. And if it sees like, hey, you never actually used the result of this, so I'm just going to skip it. Like, no, I need you to actually do this work. What it does is it loops through each of those graphs that I generated. I then say like, hey, compute the sort. And then I assign the result. And the reason I separated this onto two lines is so that I actually set like a breakpoint here when I'm doing debugging just to validate some things. So there you go. That's the simple benchmark for just the V1. And we're going to skip over the other versions. I also create this profile function, which I can call. And what it does is it creates an instance of the benchmark class, and then it will just run that benchmark repeatedly. It'll run that method again and again and again and again. And that is actually for the purpose of profiling, because I need to be able to measure the performance. I need to be able to profile the code, but if I run it just once, that's not going to be indicative of real world performance. So down here is where I would actually run everything. My apologies. And so I have the main, I take the args, I match on the first one saying like, hey, are you asking me to benchmark or not? If it is, if that first argument is benchmark, then say like, yep, first argument is benchmark, I'm going to run the benchmarks. If it's profile, then it's going to call that profile function. It's going to then take the second argument saying, okay, which version are we testing and how many loops do you want to run? And if it can't match, it's just going to throw an error. So the result of that, I'm going to scroll up here to the beginning, and I ran .NET run -c release. So I'm making sure I'm building and running in release mode. And I said, hey, I want you to benchmark. And this is the results of it running the benchmark. And I mean, you can run this for yourself, obviously, but I just want to be respectful of your time. And so baseline right now, completely naive, immutable, functional style, solving 1,000 graphs takes 55 milliseconds. Okay. So the next question is, how close or far are we from our goal? Well, 55 milliseconds, and we're running it 1,000 times. So that's 1,000 graphs. But the real world is 1,000,000 graphs. So we need to multiply this number by 1,000 to figure out how long would this actually take to solve a million. Okay, so let's see how far off we are with this. So right now it's taking 55 milliseconds to solve 1,000 graphs. So 55 milliseconds times 1 for 1,000 graphs. But we care about a million graphs. So we're going to multiply this by 1,000. So 55,000 milliseconds for 1 million graphs. Divide that by 1,000 to get it in seconds. So 55 seconds to solve 1 million graphs is our baseline right now. So that is not great. We have a ways to go, because for us, like, minimum acceptable is that we need to be able to run the whole thing in 10 seconds. Ideally, we would be able to run it within 1 second. And we are about an order of magnitude off. So we got some work to do. But what's exciting is that this is version 1, which means there's likely huge amounts of improvement that we could be making with this. So that's what the next few weeks are going to be about. It's going to be profiling this code, improving it, benchmarking it. And again, the goal is to teach you how to do these things so that you're able to kind of look at code and understand it and be able to wring even more performance out of it. So I am crazy excited. So excited I'm having a hard time talking. So if you have any questions, please feel free to hit me up in the comments or ping me on Twitter. I'd love to help. Let me know if this is a good pace for you or not, or what you're looking forward to. So until the next time, thank you very much. And let's write some fast code. Have a good day. Bye-bye.